Hello and welcome. Thank you for taking the time to join us. My name is Mark Griffiths, and as mentioned, I'm the founder and principal of Stopefill Proprietary Limited. And today I'm pleased to present this webinar titled System Design for Underground Pastefill Blockage Response. This presentation, as mentioned, is brought to you by Aranzu, designers and manufacturers of backfill and processing equipment, located in Cape Town, South Africa, and Stopefill, backfill specialists in underground mine backfill engineering and operations, based in Perth, Western Australia, where design and manufacturing excellence and operational expertise works together to provide successful outcomes for your underground mine backfill project. So, what is a blockage condition? System blockage occurs when the pressure required to initiate and maintain the flow of paste fill mixture becomes greater than the available pressure from gravity alone or pump and gravity pressure. The pressure required to maintain flow is dependent on the system physical parameters such as pipe and borehole diameter, system length, elevation changes, and system conditions such as paste buildup and loose hardened material or rocks. Maintaining flow is also dependent on fluid rheological parameters such as yield shear stress, fluid consistency index, and the flow behaviour index. An increase in either one or several of these factors will cause the flow to stall or become a local restriction, stopping flow and resulting in a blockage condition. In cemented backfill, the response time is critical. The before mentioned factors may change due to the paste fill mixture being inherently variable. Aspects such as particle size distribution, mineralogy, particle shape, binder content. These factors will change the rheological parameters such as the yield shear stress, which has an exponential relationship with the solids concentration. This means that a good quality paste mixture is close to potentially causing a blockage event, and a good system runs close to the flow limit at high solids concentrations. Other influencing factors are due to the ore body shape, the delivery pipe route will be different for each stope void. There is also a strong motivation to deliver the paste mixture at the highest solids concentration possible. This is to optimize the binder content performance, which will be the most cost-effective means to achieve early strength, to reduce the operational and personnel risk posed by the liquid paste in rush hazard. System capital cost constraints may also drive the engineering decisions and or delay the implementation of improvement opportunities. So, blockage events can occur for many reasons, including the rock borehole spalling failure, borehole casing wear through due to free fall abrasion, underground pipe or elbow failure, therefore with no driving pressure downstream, causing the downstream blockage, or the paste fill mixture friction loss increasing over time within the pipe, causing the system to stall. Paste plant operators need to have the confidence that if a blockage occurs, then they can recover the system by flushing it clear. If the system recovery is not successful, it will require the pipe to be replaced or drilled out or high pressure water blasting and may result in weeks of downtime. So some other system requirements are being able to safely and effectively isolate the immediate upstream pipework to enable the underground paste crew to manually intervene with the pipework at the blockage location. A rapid and controlled response by the paste plant operator with a procedure that can be trained and improved from learnings from each blockage event investigation. These aspects also require reliable equipment function in many upset conditions, such as power outage and associated network comms outage, and as such, the need for a manual override function to recover the underground paste fill delivery system. So during the equipment selection process, some of the equipment requirements are that it needs to be robust and reliable, that it needs to be easy to use, and the operating method simple to understand. They need to have a manual override to actuate the device. They also need to have motorised control in normal operations that can be operated from the paste plant control room and with the manual override for power outage or network outage. Needs to be compact and have manageable weight for installation, preferably on the backs to enable ease of flushing and avoid low points, and also needs to have compact size to fit in amongst the other services within the mine workings. So key pieces of the selected equipment include a diverter, which is a full pipe mechanical switching device that divert the full stream of paste flow and has no dead zones of stagnant cemented mixture that will block. Some of the functions required of a diverter is a full pipe diversion for dumping to sump for a blockage response, a quick system changeover to a new stope, upstream isolation for work crew safety, and a pressure rating of up to 20 MPa. A dump valve will enable rapid evacuation of paste mixture from the piping system in the event of a high pressure or a full blockage event. The dump valve will reseat post-actuation to enable downstream flushing. Dump valves have a pressure rating of up to 25 MPa. Both these devices can be actuated from a pressure sensor signal and provide a rapid automatic response to an imminent blockage event. The pressure limits can be adjusted by authorised personnel to suit the system's requirements and supported by a validated flow model within the fill note process. Another important piece of the puzzle are the pipeline pressure sensors, which measure the system pressure at that point and can be used to indicate when an upset flow condition is developing. The readings are also integral to the validation of the flow modelling and the calculated node pressure values. They also enable the system to measure the paste fill mixture friction loss, which is related directly to the fluid rheology. These sensors have an operating pressure of up to 100 bar. Inline flow meters measure the paste fill mixture throughput in the pipe and are extremely helpful in identifying early onset of a blockage condition. If flow is reducing with the pressure increasing, then a blockage condition is developing. It also helps in showing the blockage response is being effective. This is a key part on knowing when to apply the compressed air flush, in that you actually have mobilisation of the paste fill material before applying the air flush. If applied before the mobilisation, it can cause further compaction of the blockage paste fill mixture in the pipe. Cameras are also helpful in visual monitoring of key parts of the underground reticulation system and the stope delivery point, and also used to monitor bulkhead or paste walls and containment zones. So here you can see a basic layout of an underground paste fill system. We have in the top right-hand corner, the legend showing the pressure sensors, the diverters, the dump valves, and the control modules. So starting from the surface, we have a paste plant and a paste pump or a gravity-fed system. We have a surface borehole pressure sensor, and we have a diverter that can select one of two boreholes in this instance. We have a pressure sensor at the bottom of the underground of the boreholes in the underground workings, diverters and sumps, several downstream underground pressure sensors, dump valves, and some interlevel boreholes, and some stope delivery point dump valves. So I'll run through a mock-up and an explanation of the various functions that the equipment have, and that'll highlight the requirements of the previous information. So surface pressure sensor at the top of the borehole casing. So this can indicate borehole freefall or slack flow when a negative pressure is measured. Atmospheric pressure indicates a full column of paste in the borehole when the paste plant is running and we're delivering paste. A positive pressure indicates the pump is providing a driving pressure to the system, and the borehole and the immediate reticulation pipework is full of paste. The pressure sensor at the base of the surface borehole, they're located 20 to 30 meters away from the borehole casing breakthrough. This pressure sensor indicates the paste column height in the borehole and the system pressure at that point in the underground retic system. So the diverter at the bottom of the surface borehole, located 20 to 30 meters downstream from the borehole underground breakthrough. So this diverter dumps the full pipe cross-sectional flow of the designated to a designated sump in the event that a blockage event is detected. This protects the surface borehole and clears the upstream casing, which enables flush water to be applied to the surface to help clearing the downstream pipe work, which is particularly important for a pump system that results in a full system of paste material being delivered. In the event that there's a blockage, this initial diverter will dump the surface borehole and enable flush water to be applied to the top of the borehole. So the surface pressure sensor, the underground pressure sensor, and the diverter. So the diverter provides a mechanical isolation point to enable downstream works to be safely and effectively conducted on the underground by the underground paste crew. When switched to the dump position, the upstream system can be dumped to the sump. So the auto dump function, as shown on the slide, can be used to provide a signal, a pressure signal, to rapidly initiate the upstream system dump based on some pre-programmed limits. Dumping to a designated dump sump with barricading gates and exclusion zone signage and an optional flashing light and siren. So some of the arrangements with the friction loss. So shown here is the a flow meter, inline flow meter, sitting at the bottom of the borehole. That's sitting in a common line. So this can be used to enable a live measurement of the flow rate at that point. The inline, this is the friction loss arrangement of two pressure sensors, P1 and P2. So the difference between P1 in the upstream and P2 in the downstream, divided by the distance across them and any elevation change considerations, will provide a friction loss value. This can be used to control the system so the pressure difference divided, the operational parameters used by the paste plant control room operator to control the paste mixture rheology through solids concentration adjustment. This operational parameter indicates the paste mixture quality. So we have a dump valve here that can be used at the end of a long run, and it's a higher pressure rated dump valve at 25 MPa, and it's used to reliably evacuate the upstream paste mixture and enable a successful system flush to the dump point. The dump valve seat will reseat post-actuation, allows the application of the upstream pressure to clear to the downstream blockage recovery. So here we have a flow sensor that is located in the delivery point of the underground reticulation. And this is important to show that, that we have system flow throughout the system. And as the paste mixture from the surface mixing to the stope delivery point may be in the order of 20 to 30 minutes. So knowing that the paste is discharging at the correct rate during stope filling is an important operational parameter when making any planned adjustments. A low flow indicates that the retic may have failed and requires the underground paste crew to immediately investigate. This measurement is also used to indicate a successful flush of air and water has been achieved. This is a critical control when pouring over shift change and that no one is available to be in attendance. The downstream pressure sensors located in the downstream retic system are used to just indicate that that flow is as it is expected, and that the system is running consistently and in a stable way. Any changes will indicate to the paste plant operator that that there's been an issue, and that for the paste crew to investigate. So the equipment is used to identify the early stages of a blockage condition. Is used to clear the upstream portion of the underground reticulation. The flush water in combination with flush compressed air, and essentially repeating this method throughout the entire system. And then once cleared, paste fill can recommence. So beginning the paste fill operations, the green line indicates that we have paste flow on the surface, and it progresses to the underground, through to the stope, and we're filling the stope. In the event that we have some kind of upset condition, such as a coupling failure or a pipe failure or an interlevel borehole failure, we'll see a flow condition progressing back upstream, and an indication on the pressure sensors. This indicates to the paste plant operator that we have a blockage event, and that to bear in mind downstream from that blockage location is a stalled system with curing paste. So once the blockage has occurred, the first response steps are critical. So the entire underground system is full of cemented paste, and the dump surface hopper, to dump the surface hopper. Sorry, let me just adjust this. Okay. So we dump the surface borehole to the underground sump, and we fill the surface borehole with flush water. Following the tarps and procedures, and we contact the underground supervisor and backfill engineer. So by dumping the surface hopper, we then enable water to be applied either through the hopper itself or directly to the borehole. By dumping the diverter at the surface borehole breakthrough, that then clears the system down to that point, as indicated by the pressure sensors and a visual confirmation of paste flow to the sump. Excuse me. That immediate surface borehole and underground reticulation can then be filled with water to apply water pressure to progressively work our way down, actuate the next diverter or dump valve, and once the flow is initiated, apply the compressed air. This clears the pipework to the next dump point, and if the system does not clear, the blockage is located between these points. If the system clears, we continue this process to completely clear the system. So we move down, we've dumped out the paste material from that portion of the system, which then allows more water to be applied to the system. And we progressively work our way down until we identify where the blockage has occurred. At this point, so we identify the blockage location, and this may be caused by a dry clump of paste mixture or some loose borehole material if you're using unlined rock boreholes. And the excess upstream pressure of the applied water may be sufficient to clear the pipework. And if it is caused by the pipework coming apart, then the area can be isolated and repaired. So just here, I've noted that if a diverter was used here instead of the dump valve, you could isolate the system at that point and enable work on the level by the underground paste crew to repair this portion. If not, we then proceed upstream to the next diverter in line and isolate there. The repair gets undertaken and is repaired, and then we apply a flush down to the next diverter to remove that downstream paste mixture that would have started to cure. Progressively work our way through the system, clearing the line as we go until we ultimately clear the underground retic through to the stope, and we can recommence paste filling. So time critical recovery must be a coordinated effort for the blockage recovery. And this can sometimes require blasting, end of shift blasting to be delayed. Now, all of these procedures and tarps need to be well established and trained beforehand, and including the decision makers around things like blasting and other mining activities need to be aware of the urgency and the authority of say the request around delaying some of these activities. You know, delaying repair on the underground paste system and say blasting a production stope, the re-entry may take, you know, sufficient amount of time that the system is then unrecoverable, which could result in weeks of downtime. So it is definitely a coordinated effort, and blockage recovery will impact the mine's production. And a successful backfill operation is a result of many well-coordinated moving parts. So being paste constrained results in enormous opportunity costs for the mine. So that brings me to the end of the presentation.